Okay, so let's talk a bit about our new instrument, NIRPS and Proxima. I'm going to start speaking about the NIRPS consortium, in behalf of which I'm speaking. We are quite a lot of people. This is a picture of our next meeting, and it's basically University of Geneva, Montreal, the IAC, Porto, Grenoble, and the University of Rio Grande in Brazil. And what we've done is we built a high-resolution near-infrared spectrograph that we put at the 3.6-meter telescope in the observatory of La Silla in Chile. You can see the spectrograph here during commissioning. Now there's a thermal enclosure, so you cannot see it anymore. It's an infrared spectrograph, so YJH bands, resolution 75,000 to 9,000, AO assisted, and designed for 1 meter per second radial velocities. That's the important thing. So it has all the typical things: precise wavelength calibration, thermal stabilization, all those things. And the first target that we wanted to study with this was Proxima. I guess most of you know about Proxima. It's our lovely neighbor. You just go to the south, look at one of the brightest stars in the sky, and then turn a bit before you reach there. It's around 1/8 of the sun, 5 gigayears. It's been here since same time as we did. And it has a rotation period around 83 days, and a cycle that was suspected to be 7 years, but not exactly. And it has a planetary system that has 1 confirmed planet and 2 candidate planets. We observed this because, for us, Proxima b was the benchmark to test the capabilities of NIRPS. So we observed it for 2 years with our new spectrograph. Here you can see the radial velocities of NIRPS, along with the simultaneous radial velocities of HARPS. And before any kind of activity correction, we were getting a RMS of 1.7 meters per second with the NIRPS data. And below, you can see the variations in the full width half maximum of the lines, which we will use to track the stellar activity, mostly the rotation, that if you look carefully, maybe you can already see it around here. In addition to this, we took all the historical follow-up of this star, so we're getting 24 years of radial velocities, full width half maximum, on a ground-based photometry. So with all this, that's around almost a bit less than 4,000 data points. We have a lot to play with. And taking advantage of this, we start by defining our model, in which, same as Elizabeth was saying this morning with the transits, we're going to try to do everything at once. Our model will have at the same time the flux variation, the full width half maximum variation, and the radial velocity. We will have 0 points, a cycle, as we know Proxima has, the rotation variation, as we know Proxima has, a few terms to count for instrumental systematics, and our planets. All of it at once in a single model. And first, we're going to pretend we don't know about Proxima b. So we're going to just put this in our Gaussian process. We're going to use a multidimensional Gaussian process, which is basically the Gaussian process we've been talking about, but with a spot model in grind on it. And we're going to just put a very wide prior for our planets and see what we get. And what we get is basically a very, very significant detection of Proxima b. This looks like a periodogram, but it's not. It's a representation of the posterior distribution on a model assuming that there are 2 planets in the system. And we have this one that's very clear, and this one that I would typically not discuss because it's not super significant, but it's at a very nice period. That's the period of the candidate Proxima d. We then put this in a nice model. Well, you have it, the full model, Gaussian process, and the planets there, with a residuals of 80 centimeters per second. First time we do this kind of thing in the infrared radial velocities. And here you have assumed to the model, and I like it very much because you can see here the rotation very slowly, and then the variations of the two planets. And you can see basically that it's not just the model, the turns and twists on the data is doing them. We phase fold them, and it's basically like this. For Proxima B, 1.15 meters per second plus minus 11 centimeters per second. For D, 32 centimeters per second. It's not a complete detection, it's a bit more than 2 sigma, but it's much better than we anticipated. We also have HARPS data taken simultaneously, so we repeat the exercise, and this one becomes a little more significant. We put them in phase, and this now it's a bit more than 3 sigma. But this was not the only thing we had. We have over 24 years of data. So we go back to this, our 4,000 data points, and we do our full model, everything at once, and we pretend we don't know about the planets. And what we get with a very wide priors is that we have 2 very significant detections, Proxima B and D. So with this result, D is not a candidate any longer, but a confirmed planet. And we find nothing at the period where we expected to find Proxima C, the super-Earth at a long period. Another thing that goes a bit with a question that was asked before is we test the stability of these signals over time because the activity variations change a bit. So what we do is get our sinusoidal signal and we multiply it for a Gaussian. If the Gaussian gets defined in any part of our dataset, then the signal is in a part of our dataset. But instead of that, what we get is that both signals are flat over our complete dataset, which means they are very stable over time. And then, in particular for Proxima D, we wanted to do an additional test. It was originally found with espresso only. So we wanted to see what happens if we don't put espresso. We put everything else except espresso. And what happens is that we get the same amplitude and ephemeris in the espresso-only data and in the everything without espresso. So this is not instrument-dependent. It's not time-dependent. It's very significant, so it's a very confirmed planet now. We put everything in phase. It looks like this. This is espresso, UBES, NIRPs, and HARPS. Espresso, of course, looks better. I think it's going to take a while since we can beat that. And we get planet D with 39 plus minus 6 centimeter per second amplitude, 0.26 Earth masses, minimum mass, of course, and then planet B, 122 centimeters per second plus minus 6. And originally, I was thinking about finishing my talk here because I really like this phase-folded plot, but I thought I've said basically nothing about the Y-star. So let's add a bit, because we put 24 years of data together and we fit the cycle. If we look at the cycle, it basically looks like this. You can have it here going up and down, and it's not 7 years. It looks to be 17. We cannot fully guarantee it because with 24 years of data, 17 is not, we don't have 2 repetitions, but it's certainly not the 7 years that were proposed before. And this cycle that you can see here in a photometry also shows in the full width half maximum of the lines and a bit in the radial velocity. And I think that's the cause of the original detection of Proxima C. That's basically, it was detected using this part of the data, and I think it either is an artifact of the cycle, or we are missing on it because it gets absorbed by our cycle model. It's difficult to say, but it's not looking really good for the planet. And also taking advantage of these 24 years of data and on the fact that the rotation signal changes over time, this has already been discussed in the paper by Brad Worgeling from a few years ago. What we did was basically correct the cycle and do a sliding periodogram over our 24 years of data. And then we phase folded that with the cycle. And it looks like this. So at the beginning of your cycle, you get the rotation period. You get basically several peaks in the periodogram, strongest at 95, and as the cycle progresses, it goes towards faster cycle and then stabilizes around 38 days. If you wanted to interpret this as high latitude and equatorial, this looks a lot like the butterfly diagram of the sun, which would be an indication that Proxima behaves even more like the sun than we thought. We've done a couple more things. So if you want to check them, I would say that sadly you can't because it's under review, but you will be able to do it soon. And thank you. If there's any questions, I will take them.
Hey, Aman Carr from Georgia State. Excellent talk. Two related questions. They're similar in nature. Proxima is a high proper motion star, and when you're looking at for like a 10-year baseline, 20-year baseline, how are you decontaminating the flux from Proxima when it's going over the dense background field that it traverses over 10 years? And how are you comparing two different telescope data, like systematically? How are you able to make flux comparisons? Sorry.
We really don't have a lot of problem with contamination because there's nothing as bright as Proxima, well, except Alpha A and B, but there's nothing as bright as Proxima there. On flux, all telescopes have very similar bands, and what we are assuming is that there is a floating 0 point, so we account for any offset in the flux they would be measuring. But it's a really tiny. There's not a big difference. And in the spectrographs, they all measure different absolute velocity, but we don't really care much about that.
Early career folks in particular? I see one here. Yeah. Oh, I meant.
Old folks section, Eric Mamajek. This is a fantastic result. I love seeing the improved Proxima data. When you showed your planet table, why are the irradiances, why are the insulations uncertain? They're like 2.5 to 3 sigma. You're fixing the eccentricity. We know the luminosity. We know that. Why are the irradiance fluxes so uncertain?
It's because of the uncertainties on the stellar flux.
This is Proxima Centauri.
That's what you get from the propagation of all things.
Okay, there's no way the uncertainty in the flux, the bolometric flux for Proxima Centauri is uncertain by 30%. There's no way.
We will. So. We still under review. I will revise that.
Okay. One last quick question, if anyone has one. Someone here? Yeah. If the next speaker could come up.
When you were looking for your cycle, did you find any other periodicities that were shorter?
I mean, the cycle, let me go there. If you check, it's extremely not sinusoidal. So if you just look at periodicities, you get the cycle and half the cycle and 1/3 of the cycle and 1/4 of the cycle. Other than that, there doesn't seem to be anything other than the harmonics of the main signal.
Let's thank Alejandro one last time.